Something outran the stars over Mars. Not a glitch, not a meteor. Something fast enough to cut through the Martian night like a scalpel of light, caught by Perseverance's sky cameras in early October 2025. For just a few frames, a razor-thin streak slices across the darkness at a speed scientists could barely believe, around 60 kilometers per second. That's faster than anything built by humans, faster than most meteors that burn through Earth's skies, and eerily close to the predicted velocity of an interstellar visitor known as 3I Atlas. It happened quietly, just a faint movement against the stars, buried deep in a stack of raw images uploaded to NASA's open archive. But once an amateur astronomer noticed it, everything changed. The findings spread like wildfire across forums and research circles, stirring a mix of excitement, doubt, and something rarer, unease. Because this wasn't supposed to be possible. Not at Mars, not in that direction, and definitely not at that speed. Then came the silence. Scheduled Mars orbiter data went dark. The raw image feeds paused. No new calibration files, no follow-up posts from the mission teams. The community expected quick clarification, a statement, an update, anything. But the next batch of data never arrived. The streak became more than a curiosity. It became a mystery. But that was only the beginning. Because when one man decided to verify the data himself, the story exploded into something no one could have predicted.
The name that lit the fuse was Stefan Burns, a quiet, detail-obsessed amateur astronomer with a reputation for debunking hoaxes, not starting them. On October 2, 2025, Burns posted a 9-minute time-lapse stitched together from Perseverance's raw night sky frames. It looked ordinary at first, the usual static stars, the faint shimmer of cosmic dust, until you noticed it. A single, blade-thin streak slicing diagonally across the field. Perfectly straight, perfectly timed, and moving at an impossible pace. Burns didn't just think it was something special. He proved it. He cross-checked every frame against a fixed star catalog, making sure the rover's camera hadn't drifted. He calibrated the plate scale using known star separations, verifying the exact angle and rate of motion. Then he measured the streak's position frame by frame relative to background stars. Not once, but dozens of times. No camera glitch, no cosmic ray artifact, no dropped pixels. The numbers kept coming back the same. 60 kilometers per second. That's roughly 134,000 miles per hour, the kind of velocity reserved for interstellar objects that don't belong to the solar system. Even NASA's Parker Solar Probe, the fastest human-made object ever built, only brushes that kind of speed when it's practically skimming the sun's surface. But this streak wasn't anywhere near the sun. It was out near Mars, where the physics don't give you that kind of acceleration unless you came from somewhere far, far away. Burns was careful, painfully careful. He didn't make grand claims. He urged others to replicate or refute his findings, to stress test every pixel and every timestamp. Extraordinary claims need extraordinary calibration, he wrote. But that humility didn't stop what came next. Within hours, the post exploded across astronomy forums and social media. Tens of thousands downloaded the raw frames, rebuilt the stacks, and dove into analysis. Some confirmed the track, almost perfectly matching Burns' measurements. Others swore it was an illusion, a ghost in the data created by overstacking and digital artifacts. Arguments ignited instantly. Was this the first interstellar object caught from another planet's surface, or just a spectacular misunderstanding? Burns' name became a flashpoint. His record of precision and skepticism gave his post credibility that even professionals couldn't dismiss. For once, the amateur astronomy world wasn't chasing fantasy. It was challenging NASA's data with meticulous science. But the deeper they looked, the stranger things became. Some stacks showed faint traces beside the main streak, thinner, dimmer, and moving just as fast. Secondary flashes. Others claim to see nothing at all. The same data producing two realities. And then at 0003 UTC, a single frame showed something that defied both. A flicker of emerald light lasting less than a heartbeat. That tiny flash would divide the community more than the streak itself. And what it might represent would send scientists scrambling for explanations.
At first, most people ignored it. Just a single green pixel buried deep in a sea of stars. An imperfection, maybe, a bit of cosmic noise. But when Stefan Burns's frame stack was slowed down, that pixel came alive. A flash, faint, razor-sharp, and unmistakably green. It lasted less than a second, too brief to be coincidence, and its timing matched perfectly with the streak's passage across Perseverance's sky. That was enough to turn a technical curiosity into a full-blown obsession. Online forums exploded overnight. Some analysts swore it was a genuine emission event, a chemical signature, maybe the faint glow of a comet's tail seen from Mars for the first time. Others laughed it off, a cosmic ray strike, a hot pixel, stacking bias. Every explanation sounded possible, and that was the problem. To understand the fight, you have to know what green means in space science. When a comet glows green, it's almost always the result of dicarbon, a molecule that fluoresces bright emerald when sunlight rips its atomic bonds apart. The reaction is so predictable that comet hunters treat it like a fingerprint. See that color, and you're almost certainly seeing an active comet releasing C2 gas. But Mars complicates everything. The planet's thin atmosphere and Perseverance's sensor filters distort light in ways Earth telescopes don't. Even worse, cosmic rays constantly strike its cameras, leaving bright one-off pixels that can mimic real emissions. A single charged particle, a momentary voltage spike, and suddenly you have what looks like an alien chemical signal. Still, this flash didn't behave like a random hit. It appeared right when the streak crossed the frame at the same coordinates across multiple filtered stacks. That consistency was what kept scientists from dismissing it outright. If it were just noise, it should have appeared and vanished chaotically. But here, it tracked. That's when another twist landed. Early, unverified spectra from the Mars Express orbiter hinted at something no one expected. Almost no C2 emission at all. Instead, the readings were dominated by carbon dioxide and nickel lines, with the classic green band wavelengths practically missing. In other words, if the flash really was green, it couldn't have come from normal comet chemistry. To the professionals, that contradiction was maddening. To the internet, it was gasoline. If the color was real, it meant something else, some unknown reaction, or a contaminant never seen in comet spectra. If it was fake, it meant thousands of people had been fooled by digital artifacts for weeks. Either way, it left everyone staring at the same question. How can something glow green without the chemistry that makes it green? That question didn't just challenge observers. It forced the Mars mission teams to look closer at the one place that could hold the answer, the missing high-resolution frames from the orbiters themselves. But when those frames failed to appear, the silence spoke louder than the flash ever could.
For a few nights, Mars became the most watched patch of sky in the solar system. 3 orbiters, NASA's Mars Reconnaissance Orbiter, MRO, ESA's Trace Gas Orbiter, TGO, and Mars Express, were all lined up for a once-in-a-lifetime target. 3I by Atlas, an interstellar object skimming past Mars at tens of kilometers per second. Each spacecraft had its cameras reprogrammed, its pointing schedules rewritten, and its observation windows cut down to seconds of precision. Missing the target by even a fraction meant missing history. The plan sounded simple. In practice, it was chaos. HiRISE, MRO's powerful eye, was built to photograph rocks, cliffs, and dunes, not an object flying 30 million kilometers away, moving faster than any comet Mars had ever tracked. The team had to calculate a precise offset, leading the object's motion by fractions of a degree. Too early, and the object would be out of frame. Too late, and it would streak off into the void. Every exposure was a gamble. ESA's CSIS camera on the Trace Gas Orbiter joined the hunt too, preparing multi-band shots that might reveal a coma or tail, maybe even fragments trailing behind. Meanwhile, Mars Express's HRSC camera handled the wide-angle sweep, scanning the region for anything bright enough to break through the background stars. It was one of the most coordinated imaging campaigns Mars had ever attempted. And then, without warning, the stream of data stopped. Usually, Mars imagery trickles out fast. Even raw or uncalibrated frames hit public archives within days, giving amateur sleuths something to chew on. But this time, nothing. No new images, no calibration logs, not even low-resolution previews, just a string of technical updates about quality assurance and data validation. For a world desperate to see proof of the interstellar visitor, it felt like a blackout. The silence triggered the internet's favorite reflex: suspicion. Had the orbiters captured something too strange to release? Were they holding back images that showed multiple objects, or the fabled green flash in full color? Theories spiraled faster than facts. But inside the space agencies, the truth was far less dramatic and far more complicated. When you photograph Mars's surface, your cameras deal with slow, predictable terrain. But when you aim those same cameras at a fast-moving target millions of kilometers away, every part of the processing pipeline breaks. Cosmic ray hits, star smears, pixel drift, all of it can mimic real structure. Stack those images carelessly, and a random streak starts to look like a fragment or a jet. Release that image too early, and you risk sparking chaos. That's exactly the problem the imaging teams faced. Engineers at JPL were working frame by frame, aligning each exposure against the predicted path of 3I by Atlas, flagging every anomaly, every misregistered streak, every cosmic ray hit that might fool the eye. Each potential fragment had to be verified manually. Too cautious, and the public would accuse them of a cover-up. Too fast, and they'd risk releasing digital ghosts mistaken for alien artifacts. They were trapped between skepticism and hysteria. One anonymous team member later described it as a race against error. Every image had to survive 3 checks: geometric alignment, radiometric calibration, and cosmic ray rejection. A single false positive could make headlines and discredit months of careful work. So the data didn't vanish out of secrecy, it vanished into caution. Still, silence breeds imagination. While engineers wrestled with corrupted pixels and calibration curves, the public filled the gap with theories. Some believed the streak represented a swarm of fragments. Others whispered about energy bursts or artificial signals. The longer the archive stayed empty, the louder the rumors grew. By mid-October, no raw images had become a meme, a rallying cry, a question aimed directly at the agencies that had once promised open data. And while the scientists fought to keep credibility, the mystery took on its own life. Something had crossed Mars's sky. Of that, there was little doubt. But without those missing frames, no one could prove what it was. And every day that passed without an update pushed the story further from science and deeper into legend.